We had this example problem, and the good thing is it's an old exam problem, so it's good practice, and it's also really good practice for the homework that's due this Friday. And we worked through most of those problems. We skipped part E, partly because I haven't gotten to part I, but that's actually the same problem, but a little bit more involved. But we did everything else, and we did these calculations. And you know, if you need to, I encourage you to go back and watch the video. But what we had to do is we had these plots that I gave you. For example, the relative permeability plots. We didn't use those directly, other than maybe we used them to determine SWR and 1 minus SOR. But the relative permeability curves would have been used to create the fractional flow curves. I gave you the fractional flow curves, right? So this is fractional flow versus water saturation, typical curve. And then I gave you the derivative of that, so DFW, DSW versus water saturation. And we use those to calculate things like the saturation at the waterfront and the things like the breakthrough time and those kinds of things. What we didn't get to is part I, and let me just back up. And so ultimately what we were able to do is calculate the oil recovery at different times. And we chose 2 different times on there. On your homework, I have you do a spreadsheet and you do a bunch of times, but it's the same formula essentially for most of them, and you just drag and drop and repeat that. But one thing we didn't do is create a plot of the water saturation versus distance. And so here what I say, let me blow this up a little bit. I say on the attached graph, make a plot of, and maybe that's a typo, but it really should be SW versus XD at a certain time, 60 days. Use the following saturations to plot points on the graph. So 0.7, 0.6, 0.5, 0.4, and 0.3. Clearly indicate the position of the shock front. So, you know, if we wanted to make a whole plot, we would do a bunch of these. If I was writing a code in Python or Excel, you could just put in a bunch of points, but I've asked you to put 5 here, and then we could just connect the dots to make our plot. Now, why did I choose those saturations? Well, I chose those saturations because I know that SOR is 0.3, so I wouldn't want to choose an SW greater than 0.7. And then SWF, we calculated that to be 0.251. So I wouldn't want to do anything less than that, so I chose 0.3 as my last point. But if we go to my plot here, what I'm going to do is try to plot points. Okay, so the first position we choose is SW is equal to 0.7. That was given in the problem. So when the water saturation is 0.7, that's an SO, an oil saturation of 0.3, which is the residual oil saturation. So I know at that point, when SW is equal to 0.7, that occurs at XD is equal to 0. So that's at the front. I'm going to plot a point right there. So I don't actually have to do any calculations there. I know that SW is 0.7 is equal to SO of 0.3, my residual oil saturation. That only occurs at the very front, and then the water saturation will decrease. So let's do a more difficult one, which is SW is equal to 0.6. Okay, so I will see if I can pull this out. So it says SW is equal to 0.6, and recall that XD is equal to FW prime times TD. Well, the first thing we need is we need to know what TD is. TD is the volume injected divided by the pore volume. If it's been over a week now, but we were injecting 100 barrels per day, if you remember that. And I tell you that we're going to do it after 60 days. So the amount of volume we've injected is 100 times 60, so 6,000 barrels. And then if you recall, the pore volume, we calculated that last time, was 35,650 barrels. And that gives a dimensionless time of 0.1683. Okay, and if we compare that to the breakthrough time, which, let's see if I can recall what the breakthrough time was. I can't recall what it is right now. Maybe I'll find it in a second. But it was greater than 0.1683. So this is before breakthrough. Oh, there it is. Breakthrough was 86 days. Okay, and this is 60 days. And the dimensionless breakthrough time was about 0.223, 0.24. So this is less than the breakthrough time. So we got TD. Now we need FW prime. And we want to calculate FW prime at a specific saturation, 0.6. So what we do is we come up here. And we look at a water saturation of 0.6. We come over to over here, which is a small number. It's hard to read off of here. I think that what I should do is, and I did this on your homework, is I gave you some different scales so it's easier to read off. Otherwise, I'll have to be very lenient on the grading here. But I estimate that this is about 0.05, right? So this is 0 and 1, and this is 0.25, 0.5, 0.75. This is on the lower half. So I would put that at about 0.05, excuse me. And we could do that for other saturations, right? So if you come over at 0.5, this one's a little easier. This is about 0.25 exactly. That one's a little easier to read. At 0.4 we come up. That one's easier. That's about 0.75. At 0.3, you come up and you come across, and this is about 2.5. So now I can do those calculations. So if XD is equal to FW prime times TD, so if SW is equal to 0.7, we already knew that XD is equal to 0. If SW is equal to 0.6, then XD is equal to FW prime, which we said was, our best estimate from the plot was about 0.05. And we multiply that by TD, which is 0.1683, and we get a dimensionless distance of 0.0084. SW is 0.5, XD is 0.25 times 0.1683, which is 0.042. SW is equal to 0.4. XD is equal to 0.75 times 0.1683, which is 0.126. SW is 0.3. XD is equal to 2.5 times 0.1683, which is 0.42. So that means we made it 42% of the distance between at that saturation. And then if we wanted to do one more, we could do right at the front saturation, which we decided was 0.25. XD in that case was, and this goes back to the problem before, we calculated that FW prime was 4.13 at that value times 0.1683, which is 0.695. Okay, so we can plot those points now. I'll come back to my plot here. So at XD is equal to 0, SW is 0.7. The next one is that at XD is 0.0084. So almost like right here, it's already 0.6. So it drops pretty fast, it seems like. Okay, so it does that. I'm just estimating there. SW is equal to 0.5, occurs at 0.05, so like right about here. So it looks like it does that. Okay, so about 0.042. And then at 0.126, so right about here, SW is equal to 0.4, so it's dropping fast. SW is equal to 0.3. I'm sorry, at SW is a 0.42, so right here, SW, so now we got that. And SW is 0.25, is 0.695, so right over here. And what was, and SWR was 0.1. Okay, so what this means is that I'm going to draw this like this. Then it's going to have a shock front, come down to SWR, and it'll look like that. So this is a sketch of what the water saturation versus distance looks like at T is equal to 60 days, or TD is 0.1683. Okay. And you could make that plot for other times as well. I did write a little code that I thought I'd share with you. This is what I did on my spring break. And I can't remember if these are the exact same inputs in the problem or not. I think they might be. But what I will do is, I wrote this code in MATLAB. I could have easily written it in Python as well. And what I've done is I've gone through all the steps that we did on that example problem, or that we would anytime do to make these plots of water saturation versus distance, as well as make plots of like oil recovery versus time and whatnot. And so if I go and I run this code, actually what I did is I'm going to make the plots at different times, and I'm going to create that water saturation front. And the way I did it, it's going to be animated, so it'll move through time. So I'm going to run this. Hopefully it works out okay. So do you see that? So what happened is that this shock front was moving from left to right. And it went there, maybe I should have slowed down the code a little bit, but it went there pretty fast, and that it was like a leaky wall. So that wall was moving, pushing the oil, it was leaving some oil behind. The oil left behind is all this stuff, okay? If I waited long enough, it would recover all that mobile oil. So eventually you'd get to 70%. But I didn't run the code long enough. But let me run it one more time so we can see it here. Okay, so you see that wall moving. Once it gets to breakthrough, then all of a sudden the saturation goes up. If I were to let this go for tens of pore volumes, hundreds of pore volumes, eventually the water saturation would be 70% everywhere, meaning that I'd still have 30% oil left behind. That's even if I waited 1,000 years, because that's capillary trapped residual oil. But it would eventually get this oil over here, the oil recovery versus time. Okay. So this is a typical dimensionless oil recovery versus dimensionless time. I only went to 3 pore volumes, dimensionless time of 3. Had I gone longer, then I would have recovered more oil. Importantly, this is a straight line. And it's a straight line that's actually a 45-degree angle. It might not look that way because the scales are different, but when TD is 0.2, I have a dimensionless recovery of 0.2. Remember, it's a 1-to-1 type thing. We're assuming that our fluids are incompressible. They're at least the compressibility is small enough to make that assumption. So every time early on I inject a barrel of water, I produce a barrel of oil because SWI is equal to SWR. That water that's present is not moving. I inject water at the injector well, and at the producer well, I produce oil. It's very efficient. Once breakthrough occurs, which is right around here at about 0.25, that's when we said the breakthrough time was, all of a sudden I start producing both injected water as well as oil. And because of that, my oil recovery is slow. And it keeps going up, right? I could have gone to 4 pore volumes, 5 pore volumes, 100 pore volumes, and it would have eventually gone up to, I believe, 0.6, because it's going to be 1 minus SOR minus SWR. SOR was 0.3, SWR was 0.1. That means that this would be 0.6. So if you waited long enough, like hundreds of years maybe, you would eventually get to 0.6. But that recovery is pretty slow, right? You get your good recovery there. Over here, you know, you might still be making money because you're producing some oil and the water you're injected is cheap, but eventually that won't be the case anymore. I could also plot things like the water saturation at the producer well. So the water saturation at the producer well, oh, this might be, this does look like a slightly different problem. Maybe I had different inputs because here it's 0.2, and I think in our problem it was 0.1. But regardless, you have your initial water saturation, then when breakthrough occurs, the water saturation at the producer well increases. Now another plot I can make is the fractional flow at the producer well, which is different than the saturation. This fractional flow is a function of saturation. So when SW is equal to residual water, it's equal to 0, and then as the saturation increases, the fractional flow will increase. So let me show you that plot that I made. Okay, so this actually looks very much different. So this is the fractional flow of water at the producer well. That's why I use a subscript P. The fractional flow of water is 0 up until breakthrough time. Up until breakthrough time, the fractional flow is 0. Even though I got water present, it's immobile water. It's SWI is equal to SWR. It's immobile. All of a sudden, when breakthrough happens, the water rate increases a bunch. It goes from 0 all the way to well over 60%, and the water fractional flow goes up and up and up. Eventually, it would reach 100%, but it's not there yet. And based on your economics, you'll have to decide when to cut this off. It looks like after 3 pore volumes, you're still producing 5% oil, 95% water. You might still be making money then, okay? But when you get to 99% water or more, then you know it's going to be tough, and maybe it's time to do something different. Drill more wells, do an enhanced oil recovery routine, something like that. And based on these plots, I do think that my inputs were probably a little different than what I had in the example problem. So they don't quite match up, but the major points there are still there. Up until now, I've kind of kept it simple, and I said that the initial water saturation is equal to the residual water saturation. Now that's often true. That's often true, or at least close to being true. But it doesn't have to be, especially if you're near what's called the capillary transition zone. Something you may have learned in petrophysics and something we'll talk about later this week. But what if your initial water saturation is greater than your residual water saturation? Well, recall that we did our mass balance at the shock front, and we learned that FWF minus FWI over SWF minus SWI And then we also know from our definition of our that the derivative of the velocity is v of a saturation front is equal to the derivative of the fractional flow. And what we did is we set this equal to this because this is like a derivative, that's a derivative, and we got an equation this is at the water saturation front. And this was like a straight line, like y is equal to mx plus b. And what I did before is I said SWSI is equal to SWR, which means that the fractional flow of water initially is 0, but that's not true anymore if SWI is greater than SWR. So what that means, and this might be important for a future homework or something, that if I were to plot the fractional flow of water versus SW, it's going to look, this is SWR, this is 1 minus SOR. You'll get something like that. Right? This has got to go through at 0. And normally, we draw our tangent line from here to over there. But that's only true if SWR is equal to SWI. Let's say SWI is right here. Well, what you do is that's your starting point for your tangent. So this is FWI. And so you draw your tangent from there. You probably want a straight edge. So you draw it from there. Okay, probably should have drawn that better. But then where this touches, okay, it should only touch from one point there. That's going to be your SWF. That's your front saturation. And that's your fractional flow at your front. So that's what you do if your initial water saturation is greater than residual water saturation. You still draw a breakthrough tangent. That tangent should only touch at one point. It should just touch right at the edge. But you start it at SWI. So you start on the fractional flow curve, but at SWI, that's your initial point, and then you draw that tangent. Okay, and so of course if SWI is equal to SWR, you just start it right there and you do that, but you would get a different answer. No more questions? So the next thing is, what about gravity? So remember we have a reservoir with a dip angle. We're only talking 1D right now. Still one dimension. This alpha is the dip angle. Okay. And you could flow this direction, or you could flow in the opposite direction. Or as you learned on the exam, depending on the density difference and the dip angle and the pressure gradient, it's possible that water could flow down and oil could flow up because of the different densities. But the fractional flow equation, FW, is a little bit more complicated. This is with gravity but without capillary pressure. So 1 minus the permeability times the relative permeability of oil by the velocity, that's the total velocity, oil viscosity, delta rho, that's the difference in the water and oil densities, G sine of alpha. You divide all that by 1 plus KRO mu W, KRW mu O. So this is the fractional flow equation with gravity. Of course, if there was no gravity, if the dip angle alpha was 0, all this would go away and we have our simpler formula. But here we've got to include this. Sometimes we like to talk about the dimensionless number. You might remember that from the last chapter. That is KRO. This is the endpoint relative oil permeability, delta rho G, over velocity times the viscosity of oil. This is a ratio of gravity to viscosity. We call that the gravity number. Okay. So what is this saying? Okay, what this says is, well, if the numerator is small, then gravity is not very important. If the numerator is big compared to the denominator, then it is very important. And that makes sense. So if delta rho, if the difference in densities is very small, then you don't have much gravity segregation between oil and water. So that would be one case as to what that make that numerator small. Or if you make the denominator very big, then the gravity number would be small. So if your velocity is really high, okay, then that would make this small. So that would overcome the gravitational effect. So viscosity effects are more important than gravitational effects. But if the density difference is big and the velocity is small, much like your exam problem, then this is a significant number. It's going to be greater than 1. And you might recall from the last chapter, and if we plot FW, fractional flow, versus SW, this is SWR, this is SW is equal to 1 minus SOR, then without gravity, you get our usual plot that looks like that, right? So this is 1, that's 0, and this is no gravity. So I'll put no, yeah, so that's no gravity, okay? But you could get something like that, and this is the case where that ng naught, that gravity number, times the sine of alpha is less than 0. So that's a negative number. Okay. Or you could get a fractional flow that actually goes negative and comes up and does this. And this is for the case of ng naught sine of alpha is greater than 0. And what that really means is that we inject water up. So we start at the bottom and we inject it up. This is inject water from the top. Okay, so this is a case where you've got a reservoir that's at a dip angle, so it's at an angle. And it's got an initial water saturation, maybe it's just equal to SWR in this example. So it's got mostly oil, residual water, and I want to recover oil. And you're a reservoir engineer and you've got to decide, well, do I want to inject water from the top of the reservoir or from the bottom of the reservoir? Or does it even matter? So I'm gonna ask you, unfortunately we're not in a class together, but I want you to think for the next 30 seconds, what do you think makes more sense? What do you think will recover more oil? From injecting water from the bottom, from the top, or maybe it doesn't matter at all? And then we'll look at it here in a second. Okay, so it all comes down to our breakthrough curve. So you got to start here as WR, find the place where it crosses. So maybe it's somewhere over here. And so remember, so this would be SWF. And this is the case where we're injecting water from the top. But the one from the bottom is this curve over here. So now we got to draw a different one. So you start over here. Come down over here, and this is SWF. Okay. So try to do that yourself. Might be better to do it on a real plot. You actually, if you remember, you had a previous homework where you created these, so it might be a good idea to print them out and to do it. Maybe I should have done that, but you could print out your old homework and look at those. But the key point is SWF is higher if ng0 sine alpha is greater than 0, meaning inject water from the bottom. Okay, so the front saturation is higher because of that. So, all things considered, we plotted SW versus XD. The one case, if you inject water down, might do this. But if you inject water up, might do, you inject water from the bottom to the top, it might be that. So this is inject down, and this is inject up, so from the bottom. Clearly, injecting water from the bottom and going to the top is better. Okay, remember this is like a leaky wall. Right? It's pushing that oil from the injector to the producer, but some oil gets left behind. Importantly, less oil gets left behind if you inject water from the bottom to the top than if you inject water from the top to the bottom. I think that makes some intuitive sense. Because water is denser than oil, that if you inject from the bottom to the top, then it does a better job of pushing it up like a piston, right? So the water, gravity kind of keeps the water down, oil kind of keeps it up, so you're pushing it up and you don't have very much left behind. On the reverse side of that, if you were to try to put water in from the top, gravity would make it want to go down. It would bypass a lot of that oil, and so then you'd be leaving oil behind. And that's why we, in our leaky wall analogy, we leak more oil. The wall is more leaky if you inject from the top down to the bottom than if you inject from the bottom to the top. We've ignored capillary pressure in these calculations so far. Capillary pressure, recall, is the difference between the non-wetting and the wetting phase. We'll assume that oil is the non-wetting phase and water is the wetting phase. And remember that this is a function of water saturation. If you were to plot this, this is SOR, this is 1 minus, this is SWR, excuse me, 1 minus SOR. This is PC versus SW. There are two curves. One of them is a drainage curve, and the drainage curve is going to look something like this. This is called the capillary entry pressure. We'll talk more about it later this week. This is drainage. Remember, drainage is the non-wetting phase displacing the wetting phase. So if water is the wetting phase, this would be oil displacing water. That occurs in the formation of the reservoir. oil migrates from a source rock, migrates towards a reservoir that's full of water and pushes that water out. And it's got to overcome that capillary entry pressure to invade. We also have an imbibition curve, which looks like this. Okay, it does go negative over there. And that's what a capillary pressure curve looks like. So I do have a video that kind of discusses petrophysics, and you can always go back and look at that. But these are all things that you almost surely learned in Dr. Sharma's petrophysics class. So the importance of capillary pressure. Well, one reason why capillary pressure is important is to initialize the reservoir. We want to know what the initial conditions are in the reservoir. And by that I mean, what is the water pressure, what is the oil pressure, and what is the saturations or water saturation versus depth. Okay. So with a capillary pressure curve, you can determine what the water pressure is, the oil pressure, and then the difference is the capillary pressure, PO minus PW, and you can use the capillary pressure curve to get SW, so you can determine what the water saturation is at any depth in the reservoir. We're going to do that. We're going to do that either Wednesday or Friday, probably Friday. The second thing is, I would call it pore scale interactions and capillary trapping. Okay, so what I mean by pore scale is I mean at the grain scale. So we're like in between rocks. You learned a little bit about this in petrophysics probably too. Truth is that capillary pressure is very important at the pore scale, but many times we neglect capillary pressure at the large scale. And that seems counterintuitive. How can we neglect capillary pressure? We're not really neglecting capillary pressure at the reservoir scale. What we're actually doing is that these effects are manifested in the relative permeability curves. Okay. And you did learn this in petrophysics as well. You learned that the shape of your relative permeability curves is affected by capillary pressure and interfacial tension. If interfacial tension and capillary pressure are small, then that means that the residual saturations are small and you might go through the origin. They might be more like straight lines rather than curved lines, things like that. But the last thing we could do is sometimes we can include capillary pressure directly in our macro scale equations. So I call these the flow equations, and these were our mass balances that we derived a couple weeks ago. And they look something like dsw dtd plus fw prime dsw dxd is equal to 0. But now fractional flow includes capillary pressure as well. So we will revisit that on Wednesday and figure out how we want to include capillary pressure in there. But as a reminder, your homework is due Friday. It's my strong suggestion that you start working on that as soon as possible, especially if you have an exam later this week like I think you do. Okay?